Hello. Today we come to the end of our lessons about methods of integration. Before this lesson, we have explained a few of them, and I myself can't recall more than these types of methods of integration. Well, the first one is called substitution, and usually it's of this sort. When you have, for example, an integral of, let us say, e to the square root of x divided by square root of x dx. So your substitution would be, for example, square root of x is equal, for example, to u. And with this, this would change into e to the u du, because you have times 2. This is the first method of integration. So in other words, there are a few methods, as I said. The first one, which is the most widely used, is that you realize that perhaps a certain substitution would simplify your integral. Now, the second one is the integration by parts. And the integration by part, you notice it directly when you see two forms of functions multiplied together. Like, for example, the integral of e to the times e to the power x times x, or for example, you have x times logarithm of x, etc. With this form of integral, what you do is that you integrate one and you differentiate the other one. Let's say, for example, you integrate x, you get half x squared times the other one without change, then minus the integral of the integral of the first one times the derivative of the second one. So here you end up with what? The integral of x, which is known. Well, this is the second one. Now, sometimes you have integrals of trigonometric functions only, like, for example, tan cubic x dx, or you have, for example, sine cubic x times cosine square x dx, etc. These form of integral, we call them integration of trigonometric functions only. In other words, there is no such x here or x there, for example. Otherwise, you have to resort to another method like integration by parts. And then we spoke also when you have, for example, roots. For example, you have, for example, something like x squared divided by x squared minus 2x. Once you see a root, then you would tell yourself, now we have to remove this root. So, for example, first of all, you start by completing the square. You have here x minus 1 all square. So you get x squared minus x plus 1. So you have to subtract 1, and you end up with this integral. Then you search for the substitution. You would say, for example, I will take x minus 1 equal to secant theta. Once you do this, directly you think of the triangle. You say this is x minus 1 and this is 1. And directly here becomes x squared minus 2x. Now, your integral becomes what? Because the integral of x is equal to 1 plus sec theta all square, and the x becomes equal to sec theta tan theta d theta. And here on the denominator we have sec squared minus 1, so this all become tan theta, etc. So your integral, instead of being a function of x, it would be a function of theta, and manipulating with function of theta is easier because you know the integral of these trigonometric functions. So these are the type of methods of integration that we use. There is no such thing as methods of differentiation, but there are methods of integration, because integration is much more tedious to do, and this is why mathematicians they have tried to study each particular example and try to classify them into special kind of methods in which in each one you have to choose a certain approach, whether you substitute with a certain variable, or whether you integrate by part, or whether you transform the integral by removing the square roots, etc. And with this, these are all the methods of integration that is known. The only one which remains is the one that we are going to speak about in this lesson. Is called the method of partial fractions. And partial fractions usually deal with when you have rational functions. They are algebraic functions, like, for example, you have integral of the sort 1 over x times x plus 1 dx. How would you do? How would you go with this integral? What you do, you can write it in this form. For example, 1 over x minus 1 over x plus 1, all this dx, because here you have x minus x. You integrate this one, so directly you notice that the first one is the logarithm of x, while the second one is the logarithm of x plus 1, and there, this is your solution. this is your result. But this is easy because here you have only product of two brackets only. But sometimes you have more than this, and you have to find ways of writing your partial fraction. This is called a partial fraction. Here you have two fractions that express this simple rational function here. Because you want to isolate each denominator alone, you want to isolate each fraction alone. In other words, here you have, for example, two fractions. So you want to write them down into the form of two rational functions. Each of them, you have a simpler or a first order fraction so that you can apply directly. You look up into the table and you directly find out the integral. So in this lesson, we shall be speaking about what we call integration by parts, and this is actually our final lesson concerning the methods of integration. Now, in this lesson, we shall be first exposing the rules of partial fractions. In other words, when you have a rational function, how would you go on putting it into a sum of rational functions? Each of them you have, for example, a first order denominator. Next, we shall be explaining a method called the method of residues, because we shall see it in due time, because this is perhaps an easier method to calculate the unknowns, because we shall have to find some unknowns in order to carry on the integral. And then we shall see some integrals that can be transformed into partial fractions. And again, some integrals that are known to be difficult. How can we go on with them? Now, for the partial fractions, what the rational function that we have, they're all like the ones that we just seen here on the board. They are a rational function of x, and the denominator is composed of many brackets. Each one of them is of first degree. In other words, you have a polynomial in the numerator, another one in the denominator, and you wish to express, in order to carry on the integral of this rational, complicated rational function, what you do is that you transform it into a sum of small rational functions of first order, and each of them you can look into the table, or you know offhand directly the value of their integral. So here is, for example, you have a rational function of this form. You have here P of x is a polynomial and Q of x is a polynomial too. And of course, the coefficients are all here given. So what you do is that you decompose Q of x into the form of product of small order polynomials. For example, this is the example that we took. Here, 1 over x times x plus 1, you decompose it into a sum of two rational functions. So your integral, the one that you seek to calculate, is equal directly to the sum of these two integrals. So the first one is ln, the other one is ln x plus 1. And in this way, you can carry on the integration for the rest of the integrals if they are more complicated. If the denominator, for example, is composed of so many small brackets of polynomials, and you wish to decompose them into the sum of polynomials. Each of them is a rational function of x, but of first degree, because the denominator is of second degree. But you have here two instead of one. You have two rational functions, and each one of them, the integration is straightforward. So there is a rule for this. Here it is. Now you start with your rational function, P of x or Q of x, and you wish to decompose it into the sum of rational functions, h1 till hr, and each one of them, it's called a rational function as well, but of degree less for the denominator, less than Q of x. In fact, it's a first degree polynomial, and therefore you can easily calculate its integral. So each one of them is called, or the sum is called partial fractions, because there is no one single fraction, but there are so many fractions, and your original fraction here is decomposed into sum of fractions. So what you do is that you have to check the following. There are some rules for doing this. This is a theory, of course, that we have to follow. First of all, you have to watch out for something, that the degree of the numerator must be smaller than the degree of the denominator. In other words, you cannot have, for example, in the numerator, you cannot have, for example, something like this, x cubed plus 1 divided by x plus 1 times x minus 2, for example. You cannot start decomposing this rational function into a sum of partial fractions, unless you are sure that here you have a degree 2, therefore here it must not be more than 1. You have, for example, 1. Therefore, you can proceed onwards. But if you have degree 2 or 3, then you have to reduce the degree by first, you have to divide the numerator by the denominator in order to obtain a remainder in which their numerator is less in degree than the degree of that of the denominator. So after that, we decompose the denominator of the remainder, of course, or of your original function, which is a fractional, which is a rational function. You decompose it into into many polynomials, but each of them is of fewer degree. For example, it could be of first order, of second order, depending. For example, if the roots are complex, are not real, then you may keep them in the form of a polynomial of second order, because here, for example, you have the discriminant is negative, and therefore you cannot decompose any further this polynomial, so you keep it in this form. So you have a linear form and you have a quadratic form, and you may have, for example, a root which is repeated n times. So, and this is all the possibilities. The possibilities are that your denominator q of x can be equal to the product of a set of polynomials. Each one either is of first degree, x plus b, or of second degree, or it could be of first degree or as well equally of second degree, but you have a repeated roots or a repeated brackets. Now, if all the terms are linear, in other words, you have, for example, you have a polynomial q of x in which when you decompose it, you found it, for example, equal to x plus a1 times x plus a2 plus till x plus an. This is called, you have a product of polynomials, and each one of them is of first degree. So if it is in this form here, then your rational function can be decomposed in this form here. Here you have a root minus b1 over a1. In other words, q of x is the product of what here? a1x plus b1 times a2x plus b2 until arx plus br. But you, unfortunately, you have one polynomial which is repeated n times. So what you do, you have another set of fractions, a1 prime divided by the first one times a2 prime by the second one square, etc. And now the problem is that if you can find a way to calculate these unknowns, which are a1, a2, ar till an prime, then you can integrate your original function. Because the idea is that you cannot, or you were not able to calculate this integral. So what you do when you decompose it like this, then the integral becomes easy. Why? Because the integral of this one is the logarithm, and this is the logarithm, etc. So you can carry on the integration. So whereas if your polynomial q of x is the product of polynomials of second degree, then you do the same thing, except that the numerator in this case it's not a constant like a1, a2, but it will be of first degree. And this is the law or the rule or the theorem of partial fractions. Here is your partial fraction, your p of x over q of x will be put in this form. Now, suppose, for example, you want to evaluate this integral. It looks complicated. So what we do, we decompose the denominator in this form. Now, the idea, or the student may ask, how can we decompose this polynomial into the product of so many first order polynomials? The idea is that you have to, unless you use a numerical method, which is outside the scope of this course, you have to guess one, for example. Suppose we take one of them. For example, suppose we take this polynomial, x cubed plus 2x squared minus x minus 2. And there is a method called Horn method. And this method, if you know one guess one of the roots, then you can proceed further. What you can do is the following. You put the coefficients in a row. For example, x cubed, you have coefficient 1. Here you have 2. Here you have minus 1. And here you have minus 2. Now you guess, for example, that 1 is a root. Suppose 1 is a root. Then you put 1 here. And then you place it here. This is the first coefficient without change. Then you multiply 1 times 1. And you get 1 here. You add them up. You get 3. Again, you multiply 3 times 1. You get 3. Then you add them up, you get 2. Then you multiply 2 by 1, you get 2. Then you add them up, you get 0. If 1 is a correct root, then you must end up with a 0 remainder here. And the polynomial that you obtain now is what? Is equal to x minus 1, this is the first root, times what? Times x squared plus 3x plus 2. What is x squared plus 3x plus 2? Is the remainder here. As if you have isolated a first order polynomial, and the one which remains must be of second order, so you take the coefficient and you put them here. If you are aware that you may have another root, like for example, suppose you have minus 1 is the root, for example. So you have here again 1, 3, 2, and you put minus 1. And then you repeat the same thing. 1 comes here as it is. 1 times 1 minus 1 is equal to minus 1. You add them up, you get 2. 2 times minus 1 is minus 2. You put it here. And then you add up to 0. So it's true that now minus 1 in another root. So you have now, this can be decomposed into, again, x plus 1. And the remainder will be what? Will be x plus 2. So you have now the roots are what? 1, minus 1, and minus 2. These are the three roots. So this is one empirical way of doing, as it is here, appears here, x minus 1 times x plus 1 times x plus 2. And these are all the brackets that that you have decomposed the three order polynomial. You get three first order polynomial brackets like this. Now, what you do later on and is that your rational function shall be, according to the rule or to the law, that to the theorem of partial fractions, it can be put in the form of a1 divided by the first polynomial x minus 1 plus a2 divided by x plus 1 plus a3 divided by x plus 2. And then our task is to calculate a1, a2, a3. Because once you calculate a1, a2, a3, then it's finished, because the integral of your original rational function will be the sum of those three integrals. And these three integrals are very simple because they are all logarithmic functions of x minus 1, x plus 2, or x plus 1, or x plus 2. Now, how can we go on calculating a1, a2, a3? Now, there are various ways of doing this. The easiest is to equate both numerators. Now, the numerator on the left-hand side is equal to x squared plus x plus 4. While those at the numerator on the right-hand side, when you unify the denominator here, it will be equal to what? To a1 times x plus 1 times x plus 2, plus a2 times x minus 1 times x plus 2, and finally plus a3 times x plus 1 times x minus 1. Now here you have an identity for all values of x, and therefore you can go around by, for example, equating coefficients, for example, of a square, of x square, or of x or 4. For example, if you look into our slide here you have the coefficient of x square is equal to 1. How can you get x squared from here? You get it from multiplying x times x. So you have here on the right side you have a1, and then here you have also x squared from here, so you get plus a2. And then here also you have what? You have a3, so you have plus a3. What is the coefficient on the left-hand side? Is equal to 1. That's the first equation. While the second equation, for example, suppose we write directly the third equation, 4. There is 1 here and there is 4. This is the constant term. How do you get the constant term? You get it from here. 2 times 1, so you have 2a1. And then the constant term here, minus 2a2. Minus 2a2. And then the constant term here is what? Is minus a3. Minus a3. Let us do the second one. The coefficient of x on the is equal here. Is equal to 1. How do you get x here? 2x plus 1. You get 3. So you have 3a1. And here you get from where? Well, here you have 2x minus x. So you have plus a2. And finally, the coefficient of x here is what? There is no such x here because you have x squared minus 1. So we have now, in fact, three equations in three unknowns. The first one, a1 plus a2 plus a3, as we have written here. 1 is equal to a1 plus a2, and 4 is equal to a1 minus 2a2 minus a3, as we said. So now you have three equations in three unknowns. You solve them by any method, suppose Cramer or anything, or any method that you have had in school, and then you obtain a1, a2, and a3. Once you have a1, a2, and a3, you go back to your rational functions and you write the integral in the form of sum of partial fractions, and the integral becomes directly the sum of all the three integrals, and it's easy. Now, this is another one. For example, suppose you have here you realize that denominator, for example, you have a double root. So since you have a double root, then you have to follow the rule of partial fractions. You have a1 divided by the first polynomial x minus 1. But then when you have a double root here, you have here a2 divided by x plus 1, but you have a3 divided by x plus 1 square. And this is the law. We are not inventing something of our own. We have to follow the rules of partial fractions. When you have a double root, then you have to write it in this form. Now you seek to obtain again A1, A2, A3, and you follow the same procedure. You unify the denominator and you equate coefficients of equal powers of the numerator, and you obtain A1, A2, A3. Here are they. And when you solve them, you obtain A2 is 0, and A1 is 1, and A3 is equal to -1. You substitute again, and here is your sum of partial fractions. The first integral is easy, it's logarithm, while the second one is 1 over x plus 1. And here is your solution. Now, sometimes there is another method which is much simpler when you have simple roots. Like, for example, here, this is, suppose, for example, you have an integral of this form, and you wish to calculate the integral of the rational function on the left-hand side. And you have already decomposed the denominator into the form into 3 brackets, x minus 1 times x plus 1 times x plus 2. This is the same example that we dealt with, that we have written on the blackboard. So suppose you want to obtain A1, A2, A3. Now, instead of equating equal powers of x, you can do the following, which is easy. You can multiply both sides by x minus 1 to obtain this form here. Look, this expression here is that you multiplied both the right-hand side and the left-hand side by x minus 1. Now, when you multiply by x minus 1, this becomes A1. While here you have A2 times x minus 1, and here you have A3 times x minus 1, while here you remove the bracket which is x minus 1. Now, if you want to calculate A1, it's easy now. Why? Because you can replace here x by 1. You can substitute x by 1. So you cancel out this term as well as this term, and you end up with the value of A1. So what's the value of A1? You put here x is equal to 1. So it's 1 plus 1 plus 4. It's 6 divided by 2 times 3, 6. So A1 is equal to 1. So the way to obtain your coefficients is either, you have two methods. Either the simple method is that you can equate equal powers of x, the coefficients of the powers of x, but they have to be equal powers. For example, the coefficient x cubed here and here, or x squared here and here, and then you solve to obtain the unknowns A1, A2, A3, A4, etc. You solve n equations, n unknowns, and you obtain the coefficients. While the better way, when you have specially, but it can be, you can actually deal with this with the case or the situation when you have a double root using still this method of residue, except that it is more favorable when you have simple terms of this sort. What you do is that you multiply both sides after you decompose the denominator by the denominator of one of them. Suppose here you want, for example, A2. What you can do, suppose you want A2, then you multiply both here, this one, and here and there by x plus 1. So what you get, and then you replace x is equal to minus 1. So this cancels out and this cancels out. So directly A2 is equal to what? So A2 is equal to, here you multiply this one by x plus 1. So there remains what? There remains x squared plus x plus 4 divided by x minus 1 times x plus 2. Because we already multiplied both by x plus 1. And then you put what? You put x is equal to 1. When you put x is equal to 1, to minus 1, I'm sorry, then A1 cancels out, or I mean the term containing A1 cancels on A3, and you get directly A2. So all you have to do, just put here x is equal to minus 1. So you get here what? You get 4 minus 1, 3 plus 1 is equal to 4, divided by what? Minus 1 here, so you get minus 2, and minus 1, you get 1. So we had minus 2. Is it minus 2? We don't know. You have to check whether it's minus 2 or not. We don't know, because it's written somewhere there. But anyway, now here it is. A1 is equal to what? To the limit of you multiply the rational function by x minus 1. Because here it is. You have a rational function, p over q, and it is the summation of ai divided by x minus ri, for example. Here it is. And you want a particular value, a1, for example. What you do is that you multiply both by x minus ri, and you take the limit 1, x tends to ri. So what will happen? All the others will cancel out except your ai So all you have to do is you multiply by the denominator of the particular coefficient you wish to calculate. And this is the simple way of doing it. So here, for example, when you multiply by both sides by x minus 1, then all the other terms vanish out and you are left with a1, so a1 is equal to 1. And here you have an expression here, the one that we wrote as a matter of fact, f of x, which is p over q. In order to obtain a certain ai, one of them, you multiply both by x minus ri, and you take the limit when x tends to ri, and here it is, you get your coefficient. And this is actually much simpler, especially if you have a few number of terms, instead of going through equating the coefficients. Here, this is important. When you have, as I said before in the beginning, I said that before you start your partial fraction expansion into a sum of partial fractions, your rational function, I mean, you have to make sure first that the degree of the numerator is less than that of the denominator. Otherwise, you cannot proceed further. For example, here we have x cubed plus 2x minus 1 divided by x squared plus 2x plus 1. We cannot decompose this into partial fraction unless we end up with a first order in the numerator. So you divide by them, you get x, you have x cubed plus 2x squared plus x. You subtract, you get minus 2 x squared plus x minus 1. Again, here you have minus 2. So you have minus 2x squared minus 4x minus 2. You subtract, you have 5x minus, I suppose, plus 1. So at the end you have what? You have x minus 2 plus 5x plus 1 divided by x minus 2 plus 5 divided by x squared plus 2x plus 1. Let's see if we have calculated it correctly. Exactly. Now here, you decompose the partial fraction into, first of all, you have to do a long division in order to isolate the first term, and then you end up with the remainder. Now here you have a rational function in which the numerator is less by 1 than that of the denominator. At least it has to be less than 1. Then you can proceed now to decompose this into a partial fraction, but not before. You cannot do this before. So here you can go ahead. You can, now the denominator is equal to what? You have a double root, x plus 1 square. This is equal to x plus 1 square, and therefore your theory tells you what? Your theory tells you that you have a first term a1 divided by x plus 1 plus a2 divided by x plus 1 square, and then you may carry on equating the coefficients of equal powers of x, and here it is. This is your final decomposition, and now the integral is equal to the sum of these integrals, and these integrals is easy. Half x squared minus 2x plus 5 logarithm of x plus 4 divided by x plus 1 plus a constant, and never forget about adding a constant term. And here it is. Now there are actually integrals amenable to partial fraction. In other words, there are integrals which you can transform them into partial fraction. In other words, the problem doesn't tell you, I am a partial fraction form of functions, and please handle me in the form of partial fraction. Of course not. You seek a method in order to transform this kind of problem into a form which can be transformed later into or decomposed into partial fractions. For example, here you have sine x divided by cosine square x plus 4x plus minus 5. Here you use two types of methods of integration. The first one is a substitution method, because you directly notice here. What do you directly notice? You directly notice that this is the first form that we dealt with in the lesson of integration by substitution. Why? Because if you put cosine x is equal to u, what you get here? You get u squared plus 4u minus 5, but minus sine x dx is equal to u. In other words, this is the form of f g of x times g dash of x. What is f? F is 1 over x squared plus 4x minus 5. And what is g? It's cosine x. What is g dash? Sine x minus sine x dx, and this is why you multiply by minus sine. So this is the form directly that when you take g of x and you put equal to u. So if you substitute cosine x is equal to u, what you get? You get minus du divided by u squared plus 4u minus 5, like this. Here it is. The integral becomes equal to, you have minus du divided by u squared plus 4u minus 5. And this is directly a form which can be expanded into a partial fraction form. Why? Because you can put it in the form of this is equal to what? U plus 5 minus u minus 1. So you have to find out in fact, we can do it directly. Suppose this is this form, you have the minus sign outside, and you want to obtain here this form. So what you had, u minus 5 so you divide by minus 6, and you have here 1 and 1. So u minus u, you don't have to carry on the decomposition directly. It's u minus 1 minus u minus 5. This cancelled out. You divide by minus 6. You have minus, you have plus 6, and the integral directly is equal to the logarithm minus the logarithm. So you don't need any more. So this is a form which is amenable. It can be transformed into a partial fraction decomposition, or a method that can, in other words, you can transform this function of trigonometric expressions. You can transform them by substitution into a rational function of u instead of x, rational function of u, and therefore you can carry on the method of partial fractions. Here it is. Like we did before. This is exactly what we did. Once you end up here, then you do your partial fractions. Here the degree is 0, here the degree is 2. Then you decompose the numerator into a product of two first-order polynomial, and then you integrate each term separately. And then at the very end, when you obtain this expression, you can go back and substitute u is equal to cosine x. And here it is. Here there is 5 missing, so you have here cosine x plus 5 divided by cosine x minus 1. There are actually some integrals that we can deal with them using now we have actually we can say that we have come to the end of the method of partial fractions, but there are still really many varieties of integrals. It's not, the integrals are so varied, and this is why I told you before there are books specialized in listing types of integrals. They are not, there is no one single way of approaching integrals. So mathematicians keep on elaborating on ways to evaluate integrals. For example, suppose you have an integral of this sort. What kind of method shall we use? Shall we, for example, substitute x cubed plus 4 is equal to u? You can try. As a matter of fact, I tried myself. I can't claim that I'm an authority in finding the right or the suitable way. And no one can claim, even no instructor in the world can ever claim that he knows how to deal around except through experience. The more because I taught, for example, this subject a few times, then I know, for example, that I may approach this method, or here the method of substitution would be suitable. On the other one, I may do it through integration by parts, etc. It's not. There is no one single. It's not through a single glance like this that you come up directly with the kind of method that you shall use. It's not right. So in this, for example, what I did actually, I chose this example, and I tried myself several ways. So I tried first to put x cubed plus 4 is equal to u. So I failed. So I said, all right, this is the substitution that we have. And this substitution, what you have the following. For example, let us have this substitution. You have here the integral of x to the power 5 divided by x cubed plus 4 dx. Now what you do, I've chosen the substitution u is equal to the quadratic root 3 to the 4th root of x cubed plus 4. Meaning that I've chosen the substitution u to the power 4 is equal to x cubed plus 4. Now we shall see how can we proceed around this. Now it means that 4 u cubed du is equal to 3x squared dx. All right, so we'll see about that. Now you have here x to the power 5, and here you have a square. So you isolate x cubed, for example. You have x cubed, and then you have 3x squared dx. So x squared, there remains x squared dx. So you have here 4u cubed du divided by 3. And then here you have x cubed plus 4. to the power 1 over 4. So you have here u. All right. So now you have u square, but you have here x cube. It's complicated. So what we do is the following. This cancelled out, and you have u square. And here you have x cube. So from here, x cube is equal to what? U power 4 minus 4. So at the end, what you have here, you have 4 over 3 times the integral of u times u to the power 4 minus 4 du, and here it is. So we have succeeded. And we could not, actually, we may not have succeeded. It's not that I'm showing my competence in this. Is not true. It's in fact, I failed several times. I took by random an example, and I tried several substitutions until I found this substitution that I'm forwarding it here, and this substitution actually is the one that can handle the integral. Now again, for example, evaluate the integral of the square root of x plus 1 divided by x plus 2. Again, here what you can do in this form of integrals, you can multiply both the numerator and the denominator by x plus 1. So this becomes x plus 1, because you have square root of x plus 1 times the square root of x plus 1 divided by the square root of x plus 1 times x plus 2. This is a simple way of doing this kind of integrals. And then you can, again, complete the square here. When you complete the square here, you get, what you get here is what? First of all, I divided by 2 and I add up 2. Why? To obtain 2x plus 3. Why especially 2x plus 3? Because 2x plus 3 here is the derivative of the denominator. So what you have here, you have 1 over square root of u, 1 over the square root of g times g of x. In other words, f is 1 over the square root of x. It's a composite function with 1 over the square root of x and the function which is x squared plus 3x plus 2. And this all multiplied by g dash of x, which is the derivative of the denominator here. So this is a form which is the integral over 1 over square root of x, which is square root directly of x, and you compose it, or you obtain the composition with the function here of the denominator. So this is a form of f of g of x, g dash of x. And what remains here, what you do here then is you complete the square. And so this one, now we do it, and this one is directly a form that is standard, because once you put x plus 3 over 2 is equal to u, you get directly the x of the integral of x squared minus 4, which is again a form which is a secant minus 1 over, or as a matter of fact, it's a cosine hyperbolic function. So you can look it into the table. Now these are a list of it's for you when you encounter integrals of this sort, then you have to search for a certain substitution. So here, for example, the substitution x plus b is equal to 1 over u. I mean, these kind of tricks that instructors give to the students, they tell them, if you find an integral of this sort, then here is your substitution. Whereas if you find one of this sort, then again, here is your substitution. And when you find others like this, then these are the types of substitution that use. In other words, and sometimes even one particular substitution leads to another substitution. For example, there are problems I myself have tried. You find that you need, for example, 2 or 3 substitutions until you come to an expression which you can easily proceed onward from it, and you can carry then out the integral. So with this, as a matter of fact, we can say that we come to the end of our series of lessons on the integration of the methods of integration. So we have started by the most widely known method, which is the method of substitution, or the method of changing the variable of integration. In other words, you have an integral in terms of a function of f of x, and you transform it dx into another function f of u du, which is much simpler. This is called the method of substitution. Then there is the method of integration by parts, which you can notice on a first glance that you have a product of functions of a different nature. Then you have the method when you have square roots, then you search directly for a certain trigonometric substitution to resolve or to get rid of the root. And finally, when you have a function in the form of a rational, an algebraic or a rational function of x, then you can decompose it into a series of partial fractions. And with this, I suppose we have dealt with all the possible methods that we can use in order to calculate integrals. Of course, the idea of calculating these are methods for calculating integrals, but indefinite integrals, in other words, methods for calculating antiderivative of functions. Why we are interested in calculating antiderivatives? Because eventually we shall use the fundamental term. We are not doing this for fun or for mental exercise. We are searching. You have an application, an economic application or an engineering application or physics, whatever, in any field, and this application requires that you integrate. You have an integral from a to b f of x dx. This is a definite integral, and you wish to calculate, and you wish to use the fundamental theorem, because this is the mostly widely used. Once you want to use the fundamental theorem, then you need to calculate antiderivative of your function. Now, the method to calculate antiderivative of functions are the following, or the list of one that we have exposed. There are 3, 4 methods, and there is no more than this method, except there are a few of them that it's it's not in our course, because they're more tedious, and you can say that we have finished now all the methods, exposing all the methods for calculating antiderivatives of functions. At the end of this lesson, I wish to thank you for your attention and remind you again that all these lessons are uploaded to the site of the Uniuntunu University or Telematic University. And until we meet again, I thank you for your attention and good luck.